Welcome to the Eternon channel. This is a place for gentle science-based stories about Earth and its past, created for learning relaxation and sleep. If you find it helpful, please like and subscribe to support the channel. Now take a breath and begin. The observing window around January 6th sits inside a larger arc of time in which an unusual small body moves through the inner solar system and becomes steadily easier to follow. The name 3I Atlas identifies that body in the catalogs that track new discoveries, but the work of understanding begins far outside the object itself, in the wide geometry of where it is, how it moves, and what the Earth can see at a given moment. In this outermost region of the topic, the goal is not to decide what will happen on a single date. The goal is to define what a date can mean in observational practice and what kinds of changes are plausible as the weeks narrow toward it. A date can signal a closest approach to the Earth, a closest approach to the Sun, a change in viewing angle, a transition into a darker part of the sky, or a planned sequence of coordinated telescope time. Any of those can create the impression that something is arriving. In reality, the arrival is an alignment of circumstances that allows measurements to improve because the object grows brighter, moves across the star field at a different rate, and presents a different face of its path to instruments that must look through the moving air of the Earth and the scattered light of the sky. From the widest view, the solar system is a bright plane of activity set inside a much larger darkness. The Sun sits at the center, and the planets trace paths that are nearly in one broad disk. A small body like 3I Atlas follows its own path, and the details of that path matter because they set the pace of change in what observers can record. When the object is far away, it appears as a faint point that competes with background stars and with noise from detectors. As it comes nearer, its light grows stronger, but it also moves faster across the sky, making it harder to hold still in an image unless the telescope tracks the object rather than the stars. This creates a simple tension that shapes the outer approach window. Greater brightness tends to help measurements, but greater apparent motion can complicate them. The date January 6th can fall at a point where that balance shifts in a useful direction. The object may be bright enough to measure in shorter exposures, reducing the blur that motion creates. It may be placed in a part of the sky where fewer bright stars confuse the background. It may rise higher above the horizon at night for certain observatories, which reduces the thickness of air that the light must pass through. In the outer approach window, another constraint comes from the Earth itself. The Earth turns, and every observatory sits on a moving platform that changes its view hour by hour. Twilight, moonlight, clouds, and turbulence in the air can all limit what is possible on a given night. Even in perfect weather, the air bends and shimmers, spreading a point of light into a small disk that is broader than it would be in space. This is why many of the most precise measurements rely on space-based telescopes or on ground-based telescopes equipped with systems that correct for atmospheric blur. Yet those systems have limits, and they perform best when the object is high in the sky. The date January 6th, in an operational sense, can be a target because it is near the time when several observatories can view the object for a longer stretch of the night, or because it is near a time when the moon is less intrusive. The moon is not simply a bright disk. It adds a glow to the whole sky. For faint objects that glow can be the difference between a clear detection and a marginal one. A planned observing campaign will often be scheduled around the darker nights. Distance is a central variable in this outer region, but distance alone is not enough. There are at least two distances that matter. One is the distance from the Earth, which affects apparent brightness and apparent motion. Another is the distance from the Sun, which affects heating, and therefore any activity driven by warming. January 6th could be important because it occurs near a minimum in one of these distances, or because it occurs during a period when the distances are changing quickly. When distances change quickly, the object can brighten in a noticeable way from one night to the next, not because it alters its nature, but because the geometry improves. In the simplest case, brightness changes with the inverse square of distance. This means that a modest change in distance can create a larger change in brightness than intuition expects. Yet brightness is also shaped by the phase angle, which is the angle between the Sun, the object, and the Earth. At certain angles, the surface of a small body can reflect light more efficiently toward the Earth, or dust around it can scatter light forward in a way that makes it look brighter. This is a geometrical effect, not necessarily a physical transformation. An observing window can therefore feel event-like even when the object remains the same, because the viewing angle makes the visible light behave differently. The outer approach window also includes the limitations of prediction. The path of an object through the sky is computed from repeated positional measurements. Each measurement has uncertainty. The object is faint. The star field used as a reference has its own small uncertainties. The telescope and camera have distortions that must be corrected. When the object is first discovered, its computed orbit can change as more data arrives. Over time, the orbit becomes better constrained, but small forces can still matter. A small body that releases gas can experience a gentle push, which slightly changes its path. Even without gas release, the pressure of sunlight can alter the motion of very small fragments. In the outer window, observers treat these as possibilities that widen the range of plausible positions. The practical result is that a date like January 6th is not only a physical moment, it is also a planning marker. Observers need to know where to point their telescopes, how long to expose, and what schedule to follow. A date can be chosen because the predicted position is well constrained by then making it more efficient to allocate scarce observing time on powerful instruments. A further layer of the outer window is the question of what can be measured without assuming what the object is. At long range, the most robust measurement is astrometry, the precise position of the object against the stars. This yields an orbit and a trajectory. Photometry, the measurement of brightness, comes next. Photometry can be done through different filters that separate colors. Even then, color is not a direct statement of composition. It is a broad indicator of how the surface and any surrounding dust reflect and scatter light. Spectroscopy, which spreads light into its component wavelengths, can reveal more, but it demands a brighter signal and careful calibration. In the outer window, spectroscopy may be limited to the strongest, easiest to detect features, if any are present. The date January 6th could correspond to a time when the signal is finally strong enough for a useful spectrum, or when a larger telescope can spend enough time on the target to reach the needed sensitivity. Across this broad context, language about what is coming can be translated into a sober set of observational questions. Does the object brighten in a way that follows geometry alone, or does it brighten more than geometry predicts? Does its appearance remain star-like, or does it begin to show a faint haze around it, which would indicate material around the nucleus? Does its position follow the predicted orbit within expected uncertainty, or does it show a small drift that might hint at gentle non-gravitational forces? Does the object show a stable color over many nights, or does the color shift with time or with viewing angle? Each of these questions lives comfortably in the outer region because they can be addressed with data that does not require close physical assumptions. The outer window is therefore about building a reliable baseline. Without a baseline, any change near January 6th is hard to interpret. With a baseline, even small deviations can be recognized and described with caution. The outer approach window also sets an ethical rhythm for science communication. It encourages a separation between measurement and meaning. A date becomes important because it concentrates effort and improves conditions, not because it promises a dramatic reveal. The phrase, "What will 3i Atlas show us?" can be answered in this outer region as what the geometry and the instruments allow to be seen with higher precision. The best outcome of the window is a clearer track across the sky, a more reliable curve of brightness over time, and a better understanding of which deeper questions can be asked next without forcing conclusions beyond the evidence. In the days around January 6th, observers collect the simplest facts first and place them against the known constraints of distance, angle, and background. Only after that groundwork is solid can the attention move inward from the broad window of observation to the nearer physical processes that might shape what the object does as it continues along its path. Within the same broad observing window, the next outer layer is the object's place in space as it is known at the time of observation. 3i Atlas is not known through touch or proximity. It is known through repeated measurements of its position against the fixed pattern of stars and through the way those positions change over time. In this region, the focus stays on where it is and how it moves, not yet on what it is made of or what is happening on its surface. The object's present location is always a statement with uncertainty attached. A telescope records a frame. The frame contains stars whose positions are catalogued. The object appears as a point or a short streak, depending on the exposure and the tracking. Software compares the image to the catalog and extracts a coordinate on the sky. That coordinate is then combined with earlier coordinates to refine an orbit. The orbit is a mathematical description of motion under gravity, and it becomes more reliable as more data accumulates across nights, weeks, and different viewing geometries. The simplest description of where 3i Atlas is now begins with distance and direction. Direction is given by its coordinates on the sky, which shift from night to night. Distance is not seen directly from a single image. Distance is inferred from the orbit solution, and from parallax, the slight change in apparent position seen when observations are made from different locations or at different times as the Earth moves. When the object is relatively close, parallax becomes easier to detect, and distance estimates improve. When it is far, the parallax is small, and the uncertainty grows. This is why the approach toward January 6th matters even before any physical change is considered. If the geometry improves, The distance is pinned down more tightly, and that improves every other inference that depends on distance, including the conversion of apparent brightness into an estimate of size or activity level. Motion is the next part of the description. There is true motion through space, and there is apparent motion across the sky. Apparent motion depends on the object's velocity, its distance, and the Earth's own motion around the Sun. A fast object far away can move slowly across the sky. A moderate object close by can appear to race. For observers, apparent motion is the practical challenge. It determines how long an exposure can be before the object blurs relative to the stars, and it determines whether the telescope should track at the sidereal rate, which keeps stars sharp, or at the object's rate, which keeps the target sharp. In this region, a key element is that the object's rate of motion is not constant. It changes as the geometry changes. Near certain alignments, the object can appear to slow as its motion aligns with the line of sight. At other times, it appears to speed up when its motion is more across the observer's view. A date like January 6th can coincide with a segment of the trajectory where these apparent rates are changing quickly, forcing observers to update tracking strategies and to plan exposures that are short enough to avoid trailing, but long enough to collect sufficient light. The orbit itself is described by elements, which are parameters that define its shape and orientation. For most small bodies bound to the Sun, the orbit is an ellipse. For an object arriving from far away, the best fit can be a parabola or a hyperbola, which indicate that it is not bound and will not return in the same way. The label 3I suggests an interstellar classification, but in this region, the emphasis remains on what the measurements support. Orbit determination is sensitive to errors when the arc of observation is short. As the arc extends, the distinction between an extremely stretched ellipse and a hyperbola becomes clearer. If 3I Atlas truly follows an unbound path, its speed relative to the Sun at large distances is higher than would be expected for a body that formed within the solar system and remained bound. This is not a claim about origin in itself. It is an orbital property. The orbit also has an inclination, which describes how tilted it is relative to the plane of the planets. A high inclination can place the object on a path that crosses the planetary plane at a steep angle, affecting where in the sky it appears, and which observatories have the best view. Uncertainty is not a footnote here. It is an active part of the description. Each positional measurement has small errors. Atmospheric turbulence shifts the apparent location of a point. Detector pixels have finite size. Bright stars can saturate and distort the fit. The object can be faint, and its centroid, the estimated center of its light, can be biased by noise. If the object is surrounded by a faint haze, the centroid can shift slightly depending on how the brightness is distributed, creating a systematic error. In the outer region, observers treat the orbit solution as something that evolves. They monitor residuals, which are the differences between predicted and measured positions. Residuals that are random and small suggest the model is working. Residuals that show a pattern can indicate a missing effect, such as a small push from outgassing, or a bias in the measurements due to a faint surrounding coma. The present location also matters because it sets what can be observed. If the object is near the Sun in the sky, it is lost in glare and can be difficult or impossible to measure from the ground. If it is far from the Sun, it can be observed in a dark sky for longer hours. The elongation angle, which is the angle between the object and the sun, as seen from Earth, is therefore a practical control. Around January 6th, the object's elongation could be increasing, opening a longer nightly window. Or it could be decreasing, compressing observations into shorter times near dawn or dusk. This is why a single date can feel significant. It can mark a turn in visibility. A change of only a few degrees can mean the difference between a target that is accessible for hours and one that is accessible only briefly. Another part of the present location is the line of sight through space. The object's light passes through the interplanetary medium, a thin scattering of dust and gas within the solar system. That medium is usually too thin to matter much, but near the sun, the glow of scattered sunlight can raise the background known as zodiacal light. On some nights, the object may sit against a rich star field in the Milky Way, adding confusion and making background subtraction more difficult. On other nights, it may sit against a darker region of sky. These background differences can create subtle changes in how well brightness can be measured and how confidently a faint coma can be detected. Thus, the present location is not only a coordinate and a distance, it is also a context of background light and background sources. From this outer layer, it becomes clear why predictions around a date must be framed carefully. The object's path is a curve that is computed, refined, and checked. The most reliable statements are those that remain stable under modest changes in the orbit solution. Observers can say whether the object is moving into a better viewing geometry, whether its predicted brightness is rising due to decreasing distance, and whether its sky motion is becoming more challenging or more manageable. They can also say what kinds of measurement improvements are likely if brightness and geometry improve. Yet they cannot promise a physical reveal because physical behavior depends on internal properties not yet measured directly. The careful approach is to let the outer facts set the stage. 3i Atlas occupies a particular place moving along a particular path, with uncertainties that shrink as data accumulates. As January 6th approaches, the most honest expectation is not a surprise, but a tightening. The track across the sky becomes more precise. The distance becomes better constrained. The predicted sky position becomes more reliable. With that reliability, observers can point more powerful instruments more efficiently, and the inquiry can begin to move one step inward from motion and geometry toward the signals and measurements that carry information about the object's physical state. With the broad window established and the object's position and motion described, the next outer layer is the way astronomers turn faint light into reliable measurements. In this region, the subject is not the surface itself, but the chain of steps that carries information from the sky to a calibrated number. Every claim about 3i Atlas rests on this chain. Light leaves the object, travels across space, passes through the interplanetary dust that adds a faint glow, then enters the Earth's atmosphere, where it is bent, blurred, and sometimes absorbed before it reaches a mirror, a lens, and finally a detector. The detector does not record an object. It records counts, which are electronic responses to incoming photons. The counts must be cleaned of instrumental effects and compared to known standards. Only then can they be interpreted as a position, a brightness, a color, or a spectrum. The most fundamental measurement is astrometry, the precise position of the object on the sky. In practice, astrometry begins with an image taken by a telescope pointed at the predicted location. The field contains many stars. Those stars are not perfectly fixed points. They have proper motions, which are their slow drifts through space, and the Earth's own motion causes a shift in apparent star positions through parallax. Modern star catalogs account for these effects, but each catalog still carries tiny uncertainties that can matter when the target is faint and the margins are small. The image is processed to remove detector artifacts such as bias and dark current. Bias is an offset added by the electronics, even with no light. Dark current is a small signal generated by heat in the detector. Both must be measured and subtracted. Flat field correction follows using a reference image that reveals how sensitive each pixel is compared to its neighbors. Without this, a faint object can appear slightly brighter or fainter, depending on where it falls on the detector. After these corrections, software fits the shapes of stars to determine a mapping between pixel coordinates and sky coordinates. This mapping includes distortion terms, because a camera does not project the sky perfectly onto a flat sensor. When the mapping is established, the object's centroid is measured. The centroid is an estimate of the center of the object's light distribution. If the object is a clean point, this is straightforward. If it has a faint surrounding haze, the centroid can shift depending on the aperture used and on the background subtraction. In this way, the method itself becomes a source of uncertainty that must be tracked. Photometry comes next, because brightness is the most accessible property after position. Photometry is the measurement of how much light the object delivers through a given filter. A filter is a piece of glass that transmits a limited range of wavelengths. Filters are used because different wavelengths carry different information and because the sky background changes with wavelength. In the outer region, the first aim is consistent measurement, not subtle interpretation. Observers select an aperture which is a circular region around the object and sum the counts inside it. Then they subtract the background estimated from a surrounding annulus. The background includes sky glow, scattered moonlight, unresolved stars, and detector noise. The choice of aperture matters. A small aperture reduces background noise but can miss some of the object's light if the point spread function is broad due to atmospheric blur. A larger aperture captures more of the object's light, but adds more background noise and more contamination from nearby stars. For a fast-moving object, another complication appears. The object shifts relative to stars, so an image aligned on stars may smear the object, while an image tracked on the object may smear the stars. Some surveys choose short exposures that keep both smears small. Others take longer exposures and then stack them aligning on the object so that the object adds coherently while stars blur into trails. Each approach trades one kind of error for another. The key is that the method must be stated and repeated, because differences in method can create differences that look like physical change. Calibration is the step that turns counts into physical units. Counts depend on the telescope's mirror size, the filter's transmission, the detector's sensitivity, and the atmosphere's transparency. To calibrate observers, measure standard stars in the same field or in nearby fields with well-known magnitudes. A magnitude is a logarithmic measure of brightness. In this region, it is enough to note that a smaller magnitude means a brighter object, and that differences in magnitude correspond to multiplicative changes in brightness. By comparing the measured counts from the standard stars to their known magnitudes, observers derive a 0 point, which is the conversion factor between counts and magnitude for that night and instrument. Atmospheric extinction must also be considered. Extinction is the dimming of light by the atmosphere, and it increases when the object is observed at lower altitude where the light travels through more air. Observers correct for this, using measurements at different air masses where air mass is a measure of path length through the atmosphere. These steps can seem routine, but for a faint-moving target they are often the dominant sources of uncertainty. A small error in background subtraction or a small change in sky transparency can produce an apparent brightening or fading that has nothing to do with the object. Color measurement is photometry through multiple filters. Color is the difference between magnitudes in two filters and is a broad indicator of how the object reflects sunlight. A redder color can indicate a surface or dust that reflects more efficiently at longer wavelengths, but it can also be influenced by viewing angle and by the size distribution of dust grains. In this region, the cautious approach is to treat color as a measured property that can be compared over time. Consistency in filter choice and calibration is crucial. If different observatories use different filter sets, the colors must be transformed to a common system, which adds uncertainty. If the object is changing in brightness rapidly, color measurements must be obtained nearly simultaneously, because a change between exposures can mimic a color shift. This is why coordinated campaigns often schedule repeated sequences that cycle through filters quickly. Spectroscopy is a step deeper in measurement complexity, but still belongs to this outer region because it begins as an instrumental procedure. A spectrograph spreads incoming light into a spectrum. The spectrum is recorded as intensity versus wavelength. The raw spectrum is not immediately meaningful. It contains instrument response, atmospheric absorption features, and scattered light. Wavelength calibration is performed using known spectral lines from lamps or from the sky. Flux calibration is performed using standard stars with known spectral energy distributions. Then the spectrum can be examined for features. For a small body, features can include reflected sunlight, shaped by the surface reflectance, and if gas is present, emission bands from molecules excited by sunlight. Detecting faint gas features is difficult because they can sit on top of a bright continuum of reflected sunlight, and because the sky itself emits light at specific wavelengths. In this region, a non-detection is often as informative as a detection, but only if the sensitivity is quantified. Sensitivity depends on exposure time, telescope size, atmospheric conditions, and how the data are processed. A spectrum can look smooth and featureless, not because the object lacks gases, but because the signal is too weak to reveal them. Timing also matters. A moving target shifts in position not only between nights, but during an observing session. Accurate timing of exposures allows the predicted position to be matched and allows light curves to be constructed. A light curve is brightness versus time. Light curves can reveal periodic variations that suggest rotation, but in this region it is important to remember that periodicity can also be shaped by changing viewing geometry or by systematic effects in the measurements. A robust light curve requires repeated measurements over many hours, and preferably over multiple nights, with careful attention to calibration. When observers plan around a date like January 6th, they often seek a stretch of time when the object is visible for long enough each night to sample its brightness at many phases of its rotation, if rotation is detectable. Yet even then, the outer region requires restraint. A light curve can be consistent with rotation, but it can also be influenced by faint activity that changes the object's effective cross-section, or by the contribution of a developing coma that smooths out variations. Through all these methods, the guiding principle remains the same. Measurements are built from procedures that must be stable, repeatable, and transparent. An observing window gains meaning when it brings higher signal, better geometry, and coordinated time on instruments that can execute these procedures with enough precision. If 3-eye Atlas shows anything around January 6th, it is first seen as a change in one of these measured outputs. A shift in position, residuals, a rise or fall in calibrated brightness, a detectable extension beyond a point source, a color trend across filters, or a spectral feature above the noise. Only after these outputs are secure can interpretation move inward toward physical causes. For now, the outer region holds steady on the work of measurement itself, because it is the gate through which every later claim must pass. The sky that holds 3-eye Atlas is never empty, and the outer approach window is shaped as much by what surrounds the target as by the target itself. In this region, the background is treated as an active participant in every measurement. A camera does not see pure darkness with a single point of light. It sees a field filled with faint sources, diffuse glow and noise produced by the instrument and by the atmosphere. The task is to separate the object's signal from everything that is not the object, while keeping the process steady enough that changes across nights can be trusted. When observers plan for January 6th, they do not only consider where the object is, they consider what the sky is like where the object will be and how that sky will behave during the hours of observation. A first component of background is natural sky brightness. Even on a moonless night, the sky glows. The air emits faint light from molecules and atoms that are excited during the day by sunlight and then relax during the night. This air glow varies with time and location, sometimes changing noticeably over the course of hours. It can rise and fall in different colors, which matters because detectors respond differently across wavelengths. The sky also contains scattered light from cities and distant human activity, which increases the background and reduces contrast. In some places, a small change in haze or humidity can scatter more artificial light into the telescope line of sight. For a faint moving object, a higher background does not only make detection harder, it makes calibration more fragile because the object's counts become a smaller fraction of the total counts measured in the aperture. Subtracting a background that is large compared to the signal amplifies small errors. A tiny shift in the background estimate can create an apparent change in brightness that rivals the object's true variability. Moonlight is another dominant factor, and it acts through several mechanisms at once. The moon illuminates the ground and the air, and that light is scattered by molecules and dust in the atmosphere. The result is a brightening of the sky background that can spread far from the moon's position. The effect depends on the moon's phase and on its angle from the target, and it depends strongly on atmospheric conditions. Thin haze can turn moderate moonlight into a broad glow. Even when the moon is low, scattered light can remain. This is why observational windows often prefer darker lunar phases. Yet the moon is not the only moving source of sky brightness. The Milky Way itself contributes, especially when the target lies against its denser star fields. In those regions, the sky background is elevated not only by diffuse light, but by the combined glow of many unresolved stars. The star field is both a reference and a source of confusion. It provides the fixed pattern needed for astrometry, but it also introduces contamination into photometry. A faint star lying near the object can add counts inside the aperture. If the object moves across the sky, it passes different background stars from night to night. This creates a moving contamination that can mimic variability if it is not modeled and removed. Observers handle this by using careful background estimation and by choosing apertures that balance signal and contamination. In crowded fields, more advanced methods are used, such as fitting a model of the point spread function to separate overlapping sources. The point spread function is the characteristic shape that a point source takes on the detector, broadened by atmospheric blur and by the optics of the telescope. When the object is faint, the point spread function is not perfectly measured in the object itself, so nearby stars are used as references. Yet stars can vary in brightness and color, and detectors respond differently across the field. This is why the selection of comparison stars and the stability of the detector response remain part of the background problem. Beyond stars, there are transient artifacts. Cosmic rays strike detectors and produce bright pixels or short streaks that do not correspond to astronomical sources. Satellites and aircraft can leave trails. These can intersect the target region and bias measurements if they are not removed. Modern reduction pipelines often detect and mask such artifacts, especially when multiple images are taken and combined. When multiple exposures are stacked, the method of stacking matters. If images are aligned on stars, satellite trails remain fixed relative to the stars and can be identified. If images are aligned on the moving object, stars trail and become streaks, and satellite trails can blend into the pattern. Each choice changes which artifacts are easiest to reject. This is another way the background interacts with moving target methods. Instrument noise is not a single thing. It includes red noise, which is the uncertainty introduced by the electronics when the detector is read out. It includes dark current, which adds counts even without light. It includes pixel-to-pixel sensitivity variations that remain even after flat field correction. It includes nonlinearity, where the detector response is not perfectly proportional to the number of photons at different brightness levels. It includes charge transfer effects that can smear signals during readout. Most of these are small, but for faint targets, they are not negligible. The outer region approach is to characterize them and to propagate their effects into uncertainty estimates. Observers often report brightness with an uncertainty that reflects not only photon counting statistics, but also these systematic components. For an object like 3I Atlas, systematic errors can dominate when the background is high or when the object is near the detection threshold. Atmospheric noise adds a separate layer. Turbulence causes scintillation, a rapid flickering of starlight that can add variability to short exposures. Turbulence also changes the point spread function across time, altering how much light falls inside a fixed aperture. Water vapor and other atmospheric components absorb light at certain wavelengths, which affects spectroscopy and also affects photometry if filters overlap absorption bands. These absorption features can vary with altitude, humidity, and air mass. When the target is observed at different elevations, the amount of absorption changes. In careful observing campaigns, standard stars are observed across similar air masses, and corrections are applied. Yet the corrections are never perfect. A stable night with clear air can produce a more reliable baseline than a night with thin, high clouds that are difficult to detect, but still dim the target slightly. Such clouds can affect different wavelengths, differently introducing color shifts that are not intrinsic to the object. Zodiacal light adds another diffuse background component. It is sunlight scattered by interplanetary dust, concentrated near the plane of the solar system. In some directions, it is faint and negligible. In others, it raises the background enough to matter for faint work. The importance of zodiacal light depends on the target's elongation from the sun and its position relative to the ecliptic plane, the broad plane of planetary motion. If 3I Atlas lies near that plane during the approach window, the background can be higher. If it lies far from the plane, the zodiacal glow may be lower. This effect can shift gradually as the object moves, which means the background can change even when the moon is absent and the weather is stable. In the context of January 6th, all these background elements shape what can be asked of the data. When background is high, astrometry can remain strong because position can still be measured from a faint point, but photometry becomes less precise and faint extension, such as a delicate coma, becomes harder to confirm. When background is low, observers can push to detect subtle structure around the point, or to measure small color differences across filters. This is why a date in an observing campaign is often paired with assessments of sky quality, such as the expected moonlight level, the altitude of the target, and the star field density. It is also why the same object can look different in different reports. A survey telescope scanning quickly might report a point source and a brightness trend, while a larger telescope under darker skies might report a faint halo or a more precise color. These are not contradictions in themselves. They are expressions of different background conditions and different reduction choices. The outer region perspective treats the sky as a layered medium, not as a blank stage. The background is measured and modeled with care because the reliability of later interpretation depends on this separation. When observers describe what 3I Atlas may show in the days around January 6th, the most grounded statement is that improved background conditions, whether from darker skies, better altitude, or less crowded star fields, can allow fainter features to rise above the noise. If conditions are not improved, the object can still be tracked and characterized, but the limits remain and the measured variations must be tested against the shifting background before they are treated as intrinsic. In this way, the approach window continues to narrow with discipline, using the outer sky and its noise as the boundary that defines what can be seen and what must remain unresolved for the time being. With the observing window defined, the object located, the measurement chain described, and the sky background treated as an active constraint. The next outer layer is the simplest physical record that can be built from repeated observations, the light curve. A light curve is a time series of brightness measurements, and in the case of 3I Atlas, it serves as the first bridge from pure geometry to hints of physical state. The light curve begins as a list of calibrated magnitudes taken at known times, each with an uncertainty. It becomes meaningful when it is compared to what geometry alone predicts, and when it is examined for patterns that persist across different instruments and different nights. In this region, the inquiry remains broad. It does not claim a specific cause. It asks what the brightness does, how fast it changes, and whether the changes match known mundane drivers, such as distance and phase angle, or whether there is an excess that suggests additional processes. The baseline expectation for brightness begins with reflected sunlight. A small body is illuminated by the sun and reflects a fraction of that light. If nothing else changes, its apparent brightness rises as it approaches the Earth and the sun and falls as it recedes. The dependence on distance is strong. When the object's distance to the Earth decreases, its brightness increases roughly with the inverse square of that distance. And when its distance to the sun decreases, the illumination increases with the inverse square of the sun distance. In practice, both distances change at once, and the combined effect can produce a smooth, brightening curve. The exact curve depends on the orbit. A date like January 6th sits somewhere on that curve. If January 6th corresponds to a period of rapidly decreasing distance, the brightness can rise quickly from night to night, even if the object remains inert. If the date corresponds to a turning point where distance begins to increase, the brightness trend can flatten or reverse. Without a careful baseline model, such changes can be misread as a sudden event. The phase angle adds a second geometric driver. The phase angle determines which portion of the object's sunlit side is visible from Earth and how the scattering of light behaves. Many small bodies show an opposition effect, a brightening that occurs at very small phase angles when the Earth lies nearly in the direction of incoming sunlight. This brightening can be caused by reduced shadowing on a rough surface and by coherent backscatter, where waves of light scattered in a medium interfere constructively when returning toward the source direction. In plain terms, some surfaces look brighter when they are lit from behind the observer. Dust can also scatter light strongly forward, making an object appear brighter when the observer is near the direction of scattered light. These effects can be subtle or strong depending on the surface texture and on whether dust is present. In this region, the role of the light curve is to reveal whether brightness changes align with expected phase angle trends. If the light curve shows a hump that coincides with a particular phase angle range, that can be geometric. If the hump occurs at times where geometry predicts smooth behavior, it might suggest additional contributions such as dust. A third driver of brightness change is rotation. If the object is not spherical, its projected area changes as it rotates. A long, irregular body presents a larger cross-section at some orientations and a smaller cross-section at others, producing periodic brightness variations. The amplitude of the variation depends on shape and on viewing geometry. If the rotation axis points toward the observer, the variation can be small. If the axis is sideways, the variation can be large. In addition, surface patches of different reflectivity can create a light curve, even for a relatively round body. In this region, rotation is treated as a hypothesis that must be tested with consistency. A true rotation period should repeat with similar timing and similar shape across multiple nights once the changing geometry is accounted for. Yet even then, caution remains necessary, because observing cadence can introduce aliases, false periods, created by the pattern of observations rather than the object. For example, observing only during similar hours each night can imprint a daily rhythm. Observers address this by obtaining long, continuous runs when possible, and by combining data from different longitudes on Earth to fill gaps. When 3I Atlas is faint, the light curve is limited by noise. Each measurement has uncertainty from background subtraction calibration and instrument stability. In this region, the most important step is to distinguish real variability from scatter. Real variability will often be coherent, such as a repeating rise and fall or a sustained trend over many points. Scatter will appear random and will not correlate between independent data sets. This is why cross-checking between observatories matters. If two different instruments reducing data in different pipelines see the same trend, confidence rises. If only one sees it, it may be instrumental or environmental. Around a key date, observing campaigns often aim to increase redundancy for precisely this reason. Acclaimed brightening becomes more credible when it is seen in multiple places under different skies. The light curve also carries information about whether there is an extended component. If the object develops a coma, a cloud of gas and dust around a central nucleus, the total brightness measured in a larger aperture can rise even if the nucleus itself is unchanged. In such cases, the measured brightness depends on aperture size. A small aperture may capture mostly the nucleus, while a larger aperture captures more of the coma. Observers can exploit this by measuring brightness in several apertures. If brightness rises more strongly in larger apertures than in smaller ones, that suggests additional extended light. In this region, this is still an observational pattern, not yet a physical mechanism. It is a clue that some of the light is coming from material around the nucleus, rather than from the nucleus alone. The key is to keep the methods consistent, because changing the aperture between nights can mimic such effects. The pace of change matters as much as the presence of change. A smooth brightening over weeks can be explained by geometry and gradual activity. A sudden increase over a day or two could be caused by a change in activity, such as a new jet or fragmentation, but it could also be caused by a shift in background conditions, calibration, or contamination by a background star. In crowded fields, an object can pass near a star and appear to brighten. To guard against this, observers inspect images directly and use star catalogs to predict close passes. They may also perform difference imaging, subtracting a reference star field from new images to isolate the moving object. Difference imaging can reduce background contamination, but it introduces its own sensitivity to seeing changes and alignment errors. In this region, no single method is perfect. Robustness comes from agreement between methods. In the context of January 6th, the light curve becomes a practical forecast tool. Not a forecast of an event, but a forecast of data quality. If brightness is rising toward that date, spectra become more feasible and subtle structural searches become more sensitive. If brightness is plateauing, the date may still matter for geometry, but the gain in signal may be limited. If the light curve shows periodic variation suggestive of rotation, the date may be targeted to obtain continuous coverage that locks down a period. If the light curve shows an excess brightening beyond geometry, the date may be targeted to test whether the excess persists, grows, or fades, which can help distinguish between a sustained process and a brief episode. In this outer region, the central discipline is to treat brightness as a measured function and to build a narrative of what it does without forcing meaning. The light curve is a quiet record. It describes how much light arrives when and with what uncertainty. It can reveal patterns that are compatible with geometry, shape, and rotation, and it can reveal deviations that invite deeper inquiry. As January 6th approaches, the light curve becomes the simplest shared language across instruments and observers, a way to say with care whether 3I Atlas is behaving as expected for a distant reflecting body, or whether additional sources of light are contributing. Only after this record is stable does it make sense to move inward again from brightness patterns to the appearance of structure and the search for faint halos or tails that can turn a time series into a physical picture. After brightness is tracked as a function of time, the next measurable step remains outward in the sense that it still relies on how the object's light is distributed on the detector, rather than on any inferred interior process. This is the search for shape beyond a single point, the careful question of whether 3I Atlas looks like a bare nucleus that behaves as a point source, or whether it begins to show an extended envelope of faint material around it. In the language of small bodies, that extended envelope is called a coma, a cloud of gas and dust that surrounds a central nucleus when heating or other processes release material. In this region, the task is not to declare that a coma exists. The task is to establish how such a claim is supported, what the limits are when the signal is faint, and why a non-detection can still be consistent with several physical realities. In a perfect telescope above the atmosphere, a distant point source produces a compact diffraction pattern set by the optics. In real ground-based observations, atmospheric turbulence broadens that pattern into a seeing disk, which is the blurred image of a point. The seeing disk changes from moment to moment, and it varies across the night. A cometary coma, if present, adds a faint halo that falls off gradually with distance from the nucleus. The challenge is that a faint halo can be hidden inside the wings of the seeing disk, especially when the object is near the detection threshold. The method begins with comparison. Observers measure the object's radial profile, which is the brightness as a function of distance from the center, and compare it to the radial profile of nearby field stars in the same image. Field stars serve as empirical point sources. If the object's profile matches the stars, it behaves like a point. If the object's profile is broader than the stars, or if it shows excess brightness in the outer parts beyond what stars show that can indicate extension. This comparison must be done with care, because the point spread function can vary across the field due to optical distortions and imperfect focus. A star near the center of the image may have a slightly different profile than a star near the edge. Color matters too. The atmosphere blurs blue light differently than red light, and detectors and filters shape which wavelengths dominate the recorded signal. If the object has a different color than the comparison stars, the effective seeing can differ slightly. Observers mitigate this by selecting comparison stars near the object and by using consistent filters. They also measure the full width at half maximum, which is the width of the profile at half its peak brightness, as a compact summary of the point spread function. If the object's full width at half maximum is consistently larger than that of nearby stars across multiple exposures, this supports extension. Yet a single exposure is rarely decisive. A small focus change, a guiding error, or a brief burst of turbulence can broaden one image. The robust result comes from repeated agreement across images and nights. Another technique relies on how the object behaves under different tracking strategies. When the telescope tracks, the stars remain sharp and the moving object trails. When the telescope tracks the object remains sharp and stars trail. If the goal is to detect a coma, tracking on the object is often preferred because it preserves the object's own profile. Then the trailed stars still provide a reference for the point spread function in the direction perpendicular to their trails, and separate short exposures can provide full star profiles. When exposures are stacked aligned on the object, the nucleus adds coherently, and the coma, if present, also adds, while the stars smear into faint streaks that can be modeled and subtracted. This can increase sensitivity to faint, diffuse light. Yet stacking introduces its own assumptions about alignment accuracy. If the predicted motion rate is slightly wrong, or if the object's centroid is biased by noise, the stacked image can blur the nucleus and mimic a halo. For this reason, observers often test the method by stacking stars in the same way and checking whether an artificial halo appears. They also vary stacking parameters and verify that any detected halo remains stable. A key conceptual point in this region is that extension is not all or nothing. A coma can be present, but extremely small, confined close to the nucleus, especially if activity is weak or if the object is far from the sun. In such cases, the coma's angular size on the sky may be comparable to the seeing disk. The coma may increase the object's apparent size by only a small fraction. Detecting that requires high-signal stable seeing and careful point spread function modeling. Alternatively, a coma can be large but very faint, spreading light over many pixels. That light may be lost in the background if the sky is bright. In both cases, the absence of a visible coma does not guarantee inactivity. It can simply mean that the coma is below the detection threshold of that particular data set. Observers express this by reporting upper limits, stating how much extended light could be present without being detected given the noise. Aperture dependence in photometry provides an additional line of evidence. If the object is a pure point source, the fraction of light captured increases with aperture size in the same way it does for stars governed by the point spread function. If the object has a coma, larger apertures capture proportionally more light than expected for a point, because the coma extends beyond the core. By measuring the object in a series of apertures and comparing to stars, observers can detect an excess growth curve. This method is powerful because it reduces sensitivity to small shape differences in the core. It focuses on the outer light distribution, yet it requires careful background subtraction because larger apertures include more background noise and more contamination from faint stars. In crowded fields, the growth curve can be biased by unresolved sources. Observers address this by masking known stars, by choosing apertures that avoid contaminated pixels or by using difference images that subtract a reference star field. If a coma is detected, its morphology becomes the next descriptive step, still within this region. A symmetric coma suggests a roughly isotropic outflow of material, while an asymmetric coma can indicate localized activity or the shaping influence of sunlight and the solar wind. The solar wind is a flow of charged particles from the sun that can push ionized gas, creating a straight, narrow ion tail. Dust, which is largely neutral, is pushed mainly by sunlight through radiation pressure, which can create a broader, curved dust tail. In the present region, these are not yet interpreted as specific compositions or mechanisms. They are treated as geometry in light. The direction of any tail relative to the sun's position on the sky provides a diagnostic. A dust tail tends to point roughly away from the sun, but can curve along the object's orbit due to the combination of radiation pressure and orbital motion. An ion tail points more directly away from the sun, shaped by the magnetic field embedded in the solar wind. Observers compare tail orientation to the antisolar direction, which is the direction opposite the sun, as seen from the object projected onto the sky. When tail geometry matches these expectations, it strengthens the case that the extended light is physical rather than instrumental. The date January 6th can matter here, because the detectability of extension depends strongly on distance and phase angle. When the object is closer, any coma of a given physical size subtends a larger angular size on the sky, spreading over more pixels and potentially becoming easier to resolve. At the same time, the surface brightness of a diffuse coma does not increase as quickly as the brightness of a point source with decreasing distance, because the coma's light is spread out. Depending on how coma size evolves, the balance between point brightness and diffuse brightness can shift. Phase angle also matters because dust scattering can be forward peaked. If the viewing geometry on or near January 6th places the observer at a phase angle that enhances forward scattering, a dust coma or dust tail can appear brighter than it would at another angle. This can create a temporary enhancement of detectability that is geometric, not necessarily a change in production rate. A careful analysis therefore compares observed extension not only across time, but against changing geometry. Instrument choice shapes the search. A wide-field survey telescope may detect the object and provide regular photometry and astrometry, but its resolution may be limited and its pixel scale may smear small features. A large telescope with finer pixel scale and better seeing can detect smaller comae and faint tails. Space-based observations can bypass atmospheric blur and reach higher contrast, but space telescope time is scarce and may not coincide with every key date. For this reason, an observing campaign often combines data sources. The outer region narrative remains grounded in how each instrument samples the sky and in how claims of extension are cross-checked. A faint halo seen on one night is tested against point spread function variations, background changes, and possible contamination. If it persists across independent data sets, confidence increases. If it does not, it remains an interesting but unconfirmed hint. Non-detection, when properly framed, is also information. If repeated high-quality observations show that the object's profile matches stars within tight limits, this constrains the amount of dust and gas that can surround it at that time. It suggests that if activity exists, it is weak, confined, or composed in a way that does not produce detectable dust. Some small bodies release gas with little dust, producing weak or invisible comas in broadband imaging, while still showing spectral signatures. Conversely, dust can be present, but composed of larger grains that scatter light differently and may remain closer to the nucleus. In this region, such possibilities are acknowledged only as reasons why extension can be hard to detect, without selecting one as the explanation. Thus, the search for coma and apparent shape is a disciplined step inward from pure brightness to spatial distribution of light, still anchored in observation rather than speculation. Around January 6th, improved signal, improved geometry, and coordinated high-resolution imaging can make this step more productive. What 3i Atlas shows at this stage is not a story, but a profile, a comparison to stars, a measured excess or a measured absence. That profile sets the boundary for moving inward again. Because once the presence or absence of extended material is established within limits, the inquiry can shift from what the light looks like on the detector to what processes might produce gas and dust, and how those processes depend on heating and composition. When the object's light is tested for extension, the next observable feature that can emerge at roughly the same outer scale is directionality, a preference in where faint light goes. This is the domain of tail geometry and large-scale asymmetry, still rooted in what the image shows, rather than in claims about specific materials. A tail, if present, is not a single structure. It is a pattern produced by particles and gas that leave the vicinity of the nucleus and then respond to forces that act differently depending on size, charge, and time since release. In the outer approach window, the most reliable questions are geometric. If faint material is present, does it align with the direction away from the sun as seen from the object? Does it align instead with the direction of the object's motion along its orbit? Does it curve, broaden, or split in ways that remain consistent across repeated observations? These questions can be answered carefully, even when the signal is faint, because they depend on orientation and persistence, rather than on absolute brightness alone. The first geometric reference is the anti-solar direction, the direction on the sky, that points directly away from the sun. For any small body near the sun is the dominant source of illumination and of outward forces. If material is pushed away primarily by sunlight pressure, the faint structure tends to appear on the anti-solar side of the nucleus. If ionized gas is present, it can be guided by the solar wind, a flow of charged particles from the sun that carries a magnetic field. In that case, the resulting structure tends to be narrow and more directly aligned with the anti-solar direction, though it can show kinks or rapid changes when the solar wind changes. If dust dominates, the structure is often broader and can curve because dust particles leave the nucleus with some initial velocity and then continue along trajectories shaped by gravity and sunlight pressure. Larger dust grains respond less to sunlight pressure and remain closer to the object's orbital path. Smaller grains respond more and are pushed into a wider fan that can bend away from the orbit. A second reference is the projected direction of motion, sometimes called the velocity vector on the sky. Material released earlier can lag behind or spread along the orbit, producing a tail that appears to trail the object's path. This is especially relevant when the object is observed at long range where small angles compress three-dimensional structure into a two-dimensional projection. A dust tail can appear to point in a direction that is neither exactly antisolar nor exactly along the orbit, because the observed direction is a blend of contributions from particles of different sizes released at different times. In this outer region, the observer's job is to separate these geometric influences without forcing a single explanation. The same physical outflow can look different from different viewing angles, and a date like January 6th can coincide with a rapid change in that angle, making the apparent tail direction swing even if the outflow remains steady. Detecting a tail when the object is faint requires techniques that increase sensitivity to low surface brightness features. The tail's light is spread over many pixels, and each pixel carries noise from the sky background and the detector. One common approach is to stack many images aligned on the moving nucleus. Stacking increases the signal-to-noise ratio of features that remain fixed relative to the nucleus, such as a coma or a tail. Yet stacking can also smear features if they change during the stack interval, and it can imprint artifacts from imperfect background subtraction. Observers therefore test for consistency by creating stacks from different subsets of images and by checking whether the same structure appears with similar orientation. They also compare to control stacks of nearby stars to ensure that the processing does not create spurious streaks. When a tail is extremely faint, even a small gradient in sky background can mimic a diffuse extension. Flat field errors, scattered light, and residual star trails from imperfect masking can all produce features that resemble a weak tail. A credible detection depends on reproducibility and on alignment with physically meaningful directions, such as antisolar and orbital vectors. Once a tail or a symmetry is suspected, its orientation is measured relative to the Sun and relative to the object's motion. The Sun's position is known precisely for any time and location, so the antisolar direction on the image can be computed. The object's orbit solution provides the direction of motion. These references allow a simple test. If the feature aligns closely with the antisolar direction across multiple observations, this supports a connection to solar-driven processes. If it aligns more closely with the projected orbit direction, this supports a dust component that traces the object's path. If it lies between, the interpretation remains open, consistent with mixed dust sizes and release times. In the outer region, the value of these measurements is that they constrain what kinds of forces must be considered later. They also help distinguish a physical feature from a background artifact because the alignment is not arbitrary. A processing artifact is unlikely to persistently align with a changing antisolar direction as the object moves across the sky. Curvature is another key descriptive property. A straight feature that remains narrow can indicate a component strongly guided by the solar wind, though confirming this requires more than shape alone. A broad curved feature can indicate dust affected by sunlight pressure and gravity. Yet curvature itself is sensitive to viewing geometry. A three-dimensional curved sheet of dust can project into a straighter line when viewed edge-on. Conversely, a thin structure can appear broadened when viewed at an angle. Around January 6th, if the line of sight changes quickly, observers may see apparent changes in tail shape that are geometric. A careful analysis, therefore, compares observed curvature to predicted viewing geometry changes. If the geometry changes explain the shift, the outflow may be steady. If not, the shift may reflect changes in activity or in particle release properties. Time is embedded in tail geometry because a tail is an archive of material released earlier. Dust grains released days or weeks earlier continue to move, and their positions relative to the nucleus depend on when they were released and what forces act on them. This means the tail, if detected, can be used to infer a history of release without yet discussing interior mechanisms. Observers can model dust motion under gravity and sunlight pressure and compare the resulting predicted tail orientation to the observed one. Such modeling involves assumptions about grain sizes and release speeds, and in this outer region, those assumptions are kept broad. The aim is not to pin down a unique solution, but to test plausibility. If only extremely small grains would match the observed curvature that suggests a fine dust component. If only very large grains would match that suggests coarser dust. If a wide range of grain sizes can match, then the tail shape alone does not constrain size strongly. These are still outward-facing conclusions, because they speak about what the observed geometry permits, rather than about specific composition. Brightness gradients along a tail carry additional information, but are harder to measure reliably. The surface brightness typically falls with distance from the nucleus, because material disperses and because smaller grains can be pushed outward more rapidly. In a dust-dominated feature, the brightness may drop smoothly, while discrete jets or bursts can create knots or segments of enhanced brightness. Yet knots can also arise from background subtraction issues or from residual star trails in stacked images. A cautious approach treats any localized enhancement as tentative unless it persists across independent stacks and independent nights. If an enhancement shifts in position along the tail in a way consistent with dust motion, confidence increases. If it remains fixed in the sky, it may be a background feature. Here, the object's motion helps. Because 3I Atlas moves, background sources do not move with it. This provides a natural test. Physical structures remain tied to the nucleus, while background features do not. There is also a practical distinction between long-range and near-date tail searches. At longer distances, the tail may be smaller in angular size and harder to resolve, but the object's motion across the sky may be slower, allowing longer exposures and deeper stacks. As the object approaches, the tail may subtend a larger angle and become easier to detect geometrically, but the object can move faster, limiting exposure times and complicating stacking. Around January 6th, these factors can change the optimal strategy. Short exposures can freeze motion and preserve the nucleus profile. Many such exposures can then be stacked to recover faint, diffuse light. If the sky background is low and the object is bright enough, this approach can reveal a tail that was previously hidden. If the sky background is high, the diffuse tail may remain difficult even as the nucleus brightens, because diffuse light must compete with diffuse noise. The geometric interpretation of any detected tail must also consider projection and perspective. A tail is a three-dimensional structure. The observer sees only its projection onto the plane of the sky. The apparent length can change because the tail points partly toward or away from the observer. A tail can appear shorter even as it grows in physical length if it becomes more aligned with the line of sight. Conversely, it can appear longer if it becomes more perpendicular to the line of sight. This is why absolute tail length in images is not a stable measure of activity without modeling. Orientation and morphology, by contrast, are more robust, especially when anchored to antisolar and orbital directions that evolve predictably. In this outer region, the most disciplined outcome is a set of geometric facts. If a tail is present, its position angle on the sky can be measured, its degree of curvature, described, its persistence tested across nights, and its relationship to the sun and orbital direction assessed. If no tail is detected, upper limits can be stated in terms of surface brightness, sensitivity, and angular extent. Either way, the result narrows the path inward. A confirmed antisolar aligned feature suggests that solar-driven forces on released material are active enough to produce observable structure. A feature aligned with the orbital path suggests a dust component with grains that retain orbital memory. An absence of detectable structure suggests that any release is below the threshold for current data, or that released material does not produce strong scattering in the observed bands. Around January 6th, the value of improved geometry and improved signal is that these geometric tests can be performed with greater confidence, reducing the risk that background gradients or point spread function variations are misread as physical asymmetry. With the large-scale appearance or its limits in hand, the inquiry is prepared to cross the next boundary inward from what is seen in images to the first physical processes that can plausibly drive changes in brightness and structure as the object continues along its path. At the first inward boundary, the focus shifts from what is seen in geometry and light distribution to the environmental conditions that can act on the object and plausibly change what is observed. The central driver in the inner solar system is heating by sunlight. This does not require assuming that 3I Atlas is active. It requires describing what sunlight does to any small body as its distance to the sun decreases and as its surface experiences repeated cycles of illumination and darkness. In this region, the topic is still broad because it treats the object as a body in an external energy field. The sun delivers energy, the object absorbs some fraction, reflects some fraction, re-radiates heat, and conducts heat inward. The balance between these processes sets surface temperature patterns, and those patterns determine whether volatile substances, materials that can turn into gas at low temperatures, can begin to escape from the surface or from shallow layers. This is where the possibility of outgassing arises, but it is introduced as a consequence of environmental physics rather than as a prediction of behavior. Sunlight intensity falls with the square of distance from the sun. As the object approaches, the incoming energy per unit area rises sharply. A surface patch facing the sun heats while the shadowed side cools. If the object rotates, each patch experiences a cycle. The speed of rotation matters because it sets how long a patch stays in sunlight and how deep heat can penetrate during a single day on the object. Thermal inertia is a term used to describe how resistant a material is to temperature change, combining effects of density, heat capacity, and thermal conductivity. In simple terms, a low thermal inertia surface such as a fluffy layer of dust heats and cools, quickly producing large temperature swings. A high thermal inertia surface such as solid rock changes temperature more slowly, smoothing out swings and allowing heat to reach deeper layers. In this region, the role of thermal inertia is to explain why two objects at the same distance from the sun can behave differently in temperature and therefore in the likelihood of releasing gas. The surface temperature is also controlled by reflectivity, sometimes called albedo, which is the fraction of sunlight reflected. A darker surface absorbs more and heats more. A brighter surface absorbs less and heats less. The object's measured brightness and color provide indirect clues about reflectivity, but in this region, the connection remains cautious. Brightness in the sky depends on size, distance, and viewing angle, not only on albedo. Yet broad reflectivity differences can matter. A very dark surface can reach higher temperatures at a given distance, increasing the chance that certain volatiles will begin to sublimate, a process where a solid turns directly into gas. A more reflective surface can stay cooler, delaying sublimation. The presence of a dust layer can also insulate underlying material, limiting how quickly heat reaches buried ice. This can suppress or delay activity, or it can concentrate activity in areas where the dust layer is thinner. Different volatiles respond at different temperatures. Water ice requires relatively higher temperatures to sublimate efficiently, while carbon dioxide ice and carbon monoxide ice can sublimate at much lower temperatures and can drive activity farther from the sun. Methane and other substances can also play roles depending on composition and structure. In this region, it is enough to note that if 3I Atlas contains volatile ices, then which ices are near the surface and how they are mixed with dust will control at what distance activity might begin. The existence of activity is not assumed. The physics of phase change is described as a set of thresholds and rates. Sublimation rate increases strongly with temperature, so a small increase in temperature can produce a large increase in gas flow. This nonlinearity is one reason small bodies can show sudden changes as they approach the sun. Another reason is that the surface can evolve. If a thin crust of dust forms, it can choke off gas flow until pressure builds beneath it and finds a pathway through cracks or weak spots. If gas does escape, it can drag dust grains with it. The ability to lift grains depends on the gas flux and on the gravity of the nucleus. A small nucleus has low gravity, making it easier to lift particles. Yet the cohesion of dust, the tendency of grains to stick together, can resist lifting. Dust cohesion can be enhanced by sintering, a process where grains fuse slightly due to heat, or by ice acting as a cement. The balance between gas drag and cohesion can determine whether activity produces mostly gas with little dust or a dusty coma and tail. In this region, these are framed as possible regimes. A gas-rich dust-poor regime might produce spectral gas signatures without a strong visible coma. A dust-rich regime might produce a bright coma and tail with relatively weak gas features in visible light. The observed combination of light curve behavior extension and tail geometry sets constraints that can later be compared to these regimes. Another environmental factor is the temperature gradient with depth. Even if the surface heats during the day, deeper layers may remain cold. Heat penetrates over a thermal skin depth that depends on thermal inertia and rotation period. If volatiles lie deeper than this skin depth, they may remain stable and activity may be limited. If volatiles lie within or near the skin depth, they may respond to daily cycles, producing diurnal variations in outgassing. Such variations can create changing jets and brightness patterns. In the context of January 6th, if observations reveal periodic brightness changes or repeating asymmetries, one possible contributor could be a rotational modulation of activity. Yet this remains a possibility, not a conclusion, until other evidence supports it. The sun also produces ultraviolet radiation, which can break apart molecules and ionize gases. If gas is released, ultraviolet light can create radicals and ions that emit light at characteristic wavelengths. This is the basis for many cometary emission features. The solar wind then interacts with these ions and can shape ion tails. In this region, the key point is that solar ultraviolet radiation and the solar wind are part of the external environment. They do not require internal change in the object beyond the presence of released gas. If no gas is released, these influences have little to act on. If gas is released even weakly, they can create visible signatures under the right observational conditions. The heating environment also includes the direction of illumination. If the object's rotation axis is tilted, some regions may receive more sustained sunlight, while others remain in prolonged shadow. Seasonal effects can occur on small bodies, where different hemispheres become active at different times as the object's orientation changes along its orbit. For a rapidly moving object with an unusual orbit, the pattern of illumination can change in ways that are not typical for well-studied comets. Yet in this region, the focus stays on the principle illumination is not uniform, and the geometry of spin and orbit determines where heat is deposited. This can lead to localized activity rather than global outgassing, which in turn can produce asymmetric comae and jets. The outcome of this inward step is a physical framing of what observations around January 6th can plausibly reflect. If brightness increases beyond geometric expectations, one possibility is increased scattering from newly released dust driven by rising surface temperatures. If a coma appears, one possibility is that heating has reached volatile rich regions that begin to sublimate. If tail geometry aligns with antisolar direction and becomes more pronounced, one possibility is enhanced release of small dust grains that respond to sunlight pressure. If the object remains point-like and the brightness follows geometry closely, one possibility is that the surface is depleted in near-surface volatiles or insulated, keeping activity below detection thresholds. These possibilities are not ranked here. They are placed as a map of how the external environment can connect to the outward measurements already described. In this way, the narrative crosses the first boundary inward without jumping ahead. The outer region established what is seen and how it is measured. The present region establishes what sunlight and the near-sun environment can do in general to a small body. The next step inward is then to focus on the materials and states that could exist at and near the surface, because only by understanding plausible compositions, textures, and structures can the observed patterns of brightness, coma, and tail be connected to specific physical processes with appropriate caution. Moving one step further inward, attention turns from external heating to the materials at the surface and near surface that determine how heating is translated into observable behavior. In this region, the focus is on plausible surface layers, how they form, how they change under sunlight, and how they regulate the escape of gas and dust if volatiles are present. The surface of a small body is not a simple solid slab. It is often a composite of ice dust organics and rock fragments arranged in a porous structure. Porosity refers to empty space within the material. A highly porous surface has many voids allowing gas to move through pathways, but it also reduces thermal conductivity, which limits heat flow into depth. A less porous or more compacted layer conducts heat more efficiently, but can seal pathways inhibiting gas escape until pressure builds. A common conceptual model for a comet-like body begins with a nucleus containing a mixture of ices and dust. As it approaches the Sun, the most volatile ices sublimate, first leaving behind dust that does not evaporate. That dust can accumulate into a mantle, a surface layer of refractory material that resists sublimation. Refractory means it remains solid at the temperatures reached. This mantle can become an insulating blanket. It reduces heat penetration, protecting deeper ice, and it can also act as a cap that limits gas flow. The mantle is not necessarily uniform. It can be patchy, cracked, or disrupted by outbursts. It can include grains of different sizes. Fine grains can pack tightly and reduce permeability, while coarser grains can maintain open pathways. In this region, the importance of the mantle is that it can decouple external heating from immediate activity. An object can warm and yet remain quiet if an insulating layer prevents sunlight from reaching ice and prevents gas from escaping effectively. The formation of a mantle can also change optical properties. A dust-covered surface can be darker or redder depending on composition and grain size. Grain size affects scattering. Very fine grains can produce a smoother reflectance spectrum, while larger grains can produce different color trends. If 3I Atlas shows a color shift over time, one possible contributor in this region is changing dominance between nucleus light and dust light. Newly ejected dust in a coma can have different scattering properties than the settled surface. Yet color shifts can also be driven by geometry. Therefore, within this region, surface materials are discussed as a mechanism that can produce real changes, but the narrative does not claim that observed color changes must reflect surface evolution. Surface temperature cycles can alter the material itself. Repeated heating and cooling can cause thermal stress, cracking rock or sintered crusts. Thermal stress arises because materials expand when heated and contract when cooled. If the surface experiences large swings, cracks can open, increasing permeability and exposing fresh, volatile, rich material. This can lead to localized activity that turns on suddenly when a crack reaches a volatile pocket. Conversely, fine dust can settle into cracks and seal them again. Ice can also recondense in cold periods, acting as a cement. In this way, the surface can evolve through a cycle of opening and closing pathways. Observationally, this can produce intermittent activity where the coma appears and fades, or where brightness increases in steps. In the context of January 6th, if measurements show abrupt changes not explained by geometry or background, the surface pathway model provides one inward mechanism that could allow rapid transitions without requiring deep structural change. Another surface process is the buildup of pressure beneath a crust. If sublimation occurs below a relatively impermeable layer, gas accumulates in pores and fractures. Pressure rises until it finds a route to escape. When it does, it can carry dust and produce an outburst. Outbursts are observed in many comets and can increase brightness quickly. In this region, the physics is described as a generic possibility. The strength of the crust, the permeability, and the gas production rate set whether pressure can build. A weak crust may vent gently. A stronger crust may hold longer and then fail more abruptly. The size of the nucleus matters because gravity affects how easily dust can be lifted once a vent opens, and it affects whether fragments can separate. Yet the narrative stays within near-surface materials and does not move inward to fragmentation mechanics beyond what is needed to understand how surface layers regulate gas and dust escape. The presence of different volatile species near the surface also matters. Water ice is common in solar system comets, but carbon dioxide and carbon monoxide can drive activity at larger distances. If an object approaches from a very cold environment, it may preserve more volatile ices near the surface than a typical short-period comet that has made many close passes. Such preservation would make early activity more likely, while a depleted surface would make it less likely. For an object classified as interstellar, the history of heating can be different from that of a comet that has repeatedly approached the Sun. Yet in this region, the narrative remains cautious and uses this as a framing for why behavior could differ. It does not assert a specific history. It notes that thermal history shapes which volatiles remain near the surface and which have already been lost. A related near-surface phenomenon is the trapping and release of gases within amorphous ice. Amorphous ice is a form of water ice that forms at very low temperatures without a crystalline structure. It can trap gases within it. When it warms, it can transform into crystalline ice, releasing trapped gases. This transition can occur over a temperature range and can contribute to gas release even when water sublimation is weak. In this region, this is introduced as a plausible process that can produce gas outflow without requiring high surface temperatures. It is particularly relevant for bodies that have remained cold for long periods. If 3I Atlas shows activity at larger distances than expected, for water-driven sublimation, trapped gas release, or more volatile ices could be candidates. Again, this is not a claim about what is happening. It is a map of processes that can connect the environment to observed signals. Dust properties are equally central. Dust grains vary in size from tiny particles to larger pebbles. Their density, shape, and composition affect how they scatter light and how they respond to gas drag and sunlight pressure. Fine grains scatter light efficiently and can produce a bright coma and tail even with modest mass. Larger grains may be less efficient scatterers per unit mass and may remain close to the nucleus or follow the orbit more closely. The distribution of dust sizes can therefore shape both brightness and tail geometry. In this region, the point is that near-surface material structure influences which grain sizes are lifted. A porous surface with weak cohesion can release fine grains easily. A more consolidated surface may release fewer fine grains, producing a coma dominated by larger grains, or even a mostly gas outflow. If observations indicate a narrow ion-like tail without much dust, this could be consistent with gas-rich outflow. If observations indicate a broad dust tail, this could be consistent with fine grain production. Yet the final determination requires spectral evidence and modeling beyond this region. Near-surface materials also influence the object's rotation and its changes. If outgassing is localized, it produces a reaction force. Over time, this can change the rotation state, either speeding up or slowing down rotation, and can cause precession, a slow wobble of the rotation axis. Such changes can alter which regions face the Sun and can feed back into activity. In the current region, this is acknowledged as an inward coupling between surface venting and global behavior, but it is not pursued into detailed dynamics. The emphasis remains on the surface as a regulating interface. By the end of this region, the observational questions around January 6th can be linked to a structured set of near-surface possibilities. A steady brightening with no detectable coma can fit an inert surface and insulated mantle or activity below detection thresholds. A developing coma can fit increasing sublimation from exposed ice, the opening of pathways in a dust mantle, or the release of trapped gases. A sudden brightness increase can fit a localized failure of a crust, leading to an outburst. A change in tail geometry can fit a shift in which size grains are released, which can be influenced by surface cohesion and gas flux. Each of these links remains conditional, and each depends on careful measurement. But the move inward has narrowed the physical landscape from the broad environment to the specific interface of dust, ice, and porosity, where energy becomes gas flow and scattering structures. The next step inward is then to focus on the chemical signatures that can be detected in spectra, because spectroscopy can test whether gas is present, which species dominate, and how those species evolve with time, providing a more direct bridge between surface materials and observed light. With near-surface materials framed as the interface where heat can become gas and dust release, the next inward step is to examine what can be learned from the light that is separated into wavelengths. In this region, spectroscopy and narrowband imaging serve as the main tools because they can reveal whether the signal is dominated by reflected sunlight or whether additional emission from gases is present. The emphasis remains on what the measurements can show and how confidently they can show it. A spectrum is not a direct sample of the object. It is a pattern of intensity across wavelengths that must be interpreted through known physics of scattering and molecular emission. Yet it provides a more specific handle than broadband brightness, because different molecules and dust properties leave different signatures. For a bare, inactive nucleus, the spectrum in visible and near-infrared light is largely a reflected solar spectrum modified by the surface reflectance. The sun's spectrum contains absorption lines, which are narrow dips caused by elements in the solar atmosphere. When sunlight reflects off a surface and returns to the observer, those solar lines remain, but the overall slope and subtle broad features can change depending on the surface. A red slope means the object reflects relatively more long wavelength light than short wavelength light. Many small bodies in the outer solar system show red slopes due to complex organic materials and space weathering. Space weathering is the gradual alteration of surface materials by micrometeoroid impacts and radiation. In this region, a red slope is treated as an observational property, not as a definitive composition label. The same slope can be produced by different mixtures and grain sizes. The key is that a purely reflected spectrum should look smooth, aside from solar lines and from broad reflectance trends. If gas is present and illuminated by sunlight, additional emission features can appear. These features come from molecules that absorb sunlight and then re-emit at characteristic wavelengths, or from fragments of molecules produced by photodissociation, the breaking of molecules by ultraviolet light. The emission can be weak, and it often sits on top of the reflected continuum. Detecting it requires subtracting the continuum and correcting for atmospheric absorption. Common cometary emission species in the visible include radicals such as CN and C2, which are produced from parent molecules that may include more complex compounds. In the near-infrared water, carbon dioxide and carbon monoxide can be detected in favorable cases, often from space-based observations that avoid atmospheric absorption bands. Ground-based infrared work is possible in some windows, but is challenged by strong absorption from water vapor in Earth's atmosphere. In this region, the practical point is that the ability to detect a given molecule depends on wavelength coverage, instrument sensitivity, and observing conditions. A non-detection in one band does not imply absence overall. Spectroscopy also interacts with spatial structure. If a coma is present, the emission may be extended around the nucleus, while the reflected continuum from the nucleus remains compact. A long slit spectrograph can sample both the nucleus and the surrounding coma along a line. By comparing spectra at different distances from the nucleus, observers can test whether emission is present in the coma and how it changes with distance. If the emission grows relative to the continuum away from the nucleus, this supports a gas coma. If no emission is detected anywhere, the coma, if present, may be dust-dominated, or gas emission may be below sensitivity. Integral field spectroscopy, which records a spectrum at each point in a small field, can map emission more fully, but it is less commonly available for faint moving targets. In the context of January 6th, improved brightness and improved observing geometry can enable these spatially resolved spectral tests. A crucial part of this region is calibration and subtraction. The observed spectrum contains telluric features, which are absorption lines and bands from Earth's atmosphere. These features can be deep and can mimic or hide cometary features. Observers correct for telluric absorption by observing standard stars at similar air mass and dividing by their spectra. This works best when the atmosphere is stable. Rapid changes in water vapor can leave residuals. The instrument also has a response curve that varies with wavelength. This must be corrected to avoid artificial slopes. When the target is faint, the noise can be comparable to the expected emission lines. In this regime, careful error estimation matters. Observers may report upper limits on production rates, which are estimates of how many molecules per second would need to be released to produce a detectable line given the instrument sensitivity. These production rates depend on assumptions about excitation and outflow velocity. In this region, those assumptions are kept conservative and uncertainties are stated. Another spectral clue comes from dust itself. Dust scattering is not perfectly neutral with wavelength. Fine grains can produce a strong wavelength dependence, and the presence of certain minerals can create broad absorption bands in the near-infrared. For example, water ice can produce distinctive absorption features in the near-infrared if exposed and abundant enough. Silicates can produce features in the mid-infrared. These detections often require space-based telescopes or specialized instruments, and they depend strongly on signal. Yet even without detailed mineral bands, the spectral slope and its evolution over time can indicate changes in the relative contribution of dust coma versus nucleus surface. If a dust coma grows, the spectrum can become more dominated by dust reflectance properties, potentially changing the slope. If the dust is freshly emitted, it may show different properties than the weathered surface. Again, this is conditional. It is a way to connect observed spectral changes to physical states, without asserting a unique composition. Time variation in spectral features is also central. If activity is driven by heat and gas emission, may strengthen as the object approaches the sun and weaken as it recedes. If activity is episodic, emission may appear briefly. If different volatile species dominate at different temperatures, the relative strengths of features can shift. For instance, more volatile species could dominate at larger distances, while water-related features become